Hi everyone, welcome to my presentation at the Knowledge Graph Conference 2021. My name is Alena, I'm a computational linguist at Coreon, and today I'm going to talk about Coreon's approach to data taxonomization. It's no secret that AI has been pretty successful at tackling different NLP tasks recently, so we embarked on a little journey of our own, hoping to find an efficient machine learning-powered solution for taxonomy drafting that would make the life of taxonomists just a bit easier. So today I'll walk you through our taxonomization quest and demonstrate what we achieved on the example of interactive terminology for Europe, IATA. Before I start, a few words about Coreon. Coreon is a Berlin-based unique taxonomy ontology management software system solution that caters for the needs of large-scale knowledge repositories. We unify knowledge with language by combining concept maps, which are technically knowledge graphs, with concept-oriented language-agnostic terminology modeling. We strive to convert data into knowledge and to provide an intuitive and user-friendly environment for its management. So, in case you are not working in the NLP domain and never heard of taxonomies and need a visual clue what the talk is going to be about, here it is. I'll be talking about Coreon's strategy to conversion of unstructured haystack of concepts into a structured graph-like scheme, taxonomy. In essence, we'll see how AI can lend taxonomists a hand in their daily work. I'll briefly introduce the resource we got for taxonomization and walk you through our study and two approaches that we chose to test. We'll talk about the benefits of our collaborative AI approach and briefly have a look at a typical industry scenario to show you how these drafted taxonomies can be leveraged in practice. All right, to begin with, let's talk about structured data. Structured data is a highly organized and can be understood by machine language. Its most attractive feature is that we can straightforwardly manipulate it, as well as link it, extend it, and search it. Another forte of structured data is that it is very comprehensive. It provides useful information, as well as helps algorithms and companies rely on more than only paper-based systems. And this is how we move to our precious resource, interactive terminology for Europe, or shortly IATA. IATA holds a large part of the textual knowledge of the European Union and has almost 1 million concepts. It also stores multilingual terms and loads of metadata. However, there is a problem. IATA can only be accessed lexically, and while database concepts have some cross-links and metadata, they still kind of stand alone. So we thought, what can be done to bring in some structure? What if IATA were taxonomized? Taxonomization here is linking of related concepts into knowledge graphs, resulting in a full-fledged ontology. This way, the data could not only be consumed by linguists, but would also become accessible, let's say, through a machine-readable Sparkle endpoint. It will become a powerful resource for AI projects, particularly within a segment of small and medium enterprises that rarely have the means to create multilingual formalized knowledge of their own. So our objective was to investigate if, given recent scientific advances, we could facilitate a speedy creation of a deeply structured taxonomy. Basically, we want to turn a flat set of concepts without relations between them into a hierarchical, machine-accessible knowledge graph. To test our hypothesis, we chose two scenarios, manual and semi-automatic taxonomization. In the first scenario, a linguist took a flat list of concepts and turned them into a structured taxonomy, establishing broad and narrower relations between the concepts. In the second scenario, a machine learning-powered algorithm drafted this taxonomy, and it was later curated by a linguist. In both cases, the taxonomies feature not only initial input concepts, but also the established relations between them and higher-level parent nodes that bring meaningful structure into the taxonomy. I want to emphasize here that we did not aim for an in-depth review of semantic coherence within the resulted concept clusters. We rather focus on comparison of measurable parameters such as working hours, amount of transactions in the software, and number of relations created. To make taxonomies a bit comparable, we established that both shall share 5 identical top-level nodes, and parent nodes may not have more than 20 to 25 children. Of course, the exported input concepts were identical, and our curators are not domain knowledge experts, yet they were pretty familiar with the used software. When approaching manual taxonomization, Curator's strategy was to move from concept to concept, starting from the top-level nodes and establishing broader, narrower relations, later dividing the nodes further down in subtrees. This top-down method requires several passes through the data, going from general to specific. The curator was also exploiting the metadata of the terms, just like on this concept card for the abnormal mortality. Corion's concept card is a preview widget for the whole concept information. It usually contains the terms of the two currently selected languages, like German and English here, domain values as statistics and demography and population here, as well as the definition to give a quick encyclopedic-like hint of what a concept is about. Since initially concepts were sorted alphabetically, the taxonomists had to constantly jump from one context to another that would most likely be semantically far away. Of course, the Taxonomy software provides a set of capabilities and interaction functionalities to comfortably restructure the data. Like here, we see the concept inflammation being dragged from diseases to immune system. So the red dotted line shows the relations to be deleted, and the green solid line is the new relation being established. This highly visual feedback helps the taxonomist to review the effect of the drag and drop before confirming the action. While being a tedious challenge, the created taxonomy is a pure result of the intellectual human capacity, not influenced by any additional obscure models or primed by pre-trained algorithms. For automatic taxonomy induction, we came up with a combination of several algorithms. We used terms and synonyms comprising each IATA COVID concept as an input data. First, input is vectorized, so text tokens representing each concept are converted into dense vectors of numbers. Here we used a pre-trained and publicly available fast text word embeddings to convert terms to vectors. Next, we calculate a pairwise constant similarity for all combinations, forming a symmetric matrix of similarities. And to create a graph, each node is represented by an input concept. To form the vertices of the graph, we establish a threshold, and if two concepts have a similarity higher than the determined threshold, an edge is formed between the nodes that correspond to these two concepts. The formed edge will then have a similarity score as a weight attribute. Ultimately, all combinations of concept nodes are checked to see whether a connection between them will be formed, hence resulting in a non-directed weighted graph. Subsequently, we use a community detecting algorithm, Louvain, in this case. So we use it on the graph to reveal nodes that are more closely related than others. And the process is executed recursively in order to further break down clusters into subclusters. The produced taxonomy starts with a root node and expands until leaf nodes reach the input concepts. The automatically generated intermediate branch nodes are labeled with temporary IDs that are to be named manually after. The algorithm is essentially forming concept clusters as concept nodes form clusters with a common parent node. Also, neighboring clusters are semantically closer than clusters farther apart in the taxonomy. The resultant taxonomy was revised by a curator, and in contrast to manual taxonomization, the curator started with the proposed taxonomy, meaning all COVID concepts became leaf nodes, and the higher level suggested nodes had unsigned temporary labels, placeholders such as temp IDs, 1, 2, and so on. So input concepts became leaf nodes grouped into the generated 55 higher level nodes with unassigned temporary labels. The curator's approach was to traverse clustered leaf nodes and assign meaningful names to each of the 55 parent concepts, replacing temporary labels. Even though we did not quantify the semantic soundness of the generated clusters, most of them were pretty okay. For example, this cluster with temporary ID 69 required no curation whatsoever, only naming. Of course, there were grouping errors likely triggered by corpora used to pre-train fast text. Like here, you see interstitial space, which is space between cells, and hospital, pharmacy. These two concepts were wrongly clustered together. As for word embeddings, both concepts are spaces appearing in the similar semantic neighborhoods. Some existing concepts became parent concepts as well. For instance, the curator decided to make the existing containment measures concept the parent of a civil confinement, disinfection, infection control, and quarantine. Here you see a part of the backbone of the resulting semi-automatically created taxonomy. When we look at the pure task, namely to name the clusters, clean them semantically, and to finalize the draft taxonomy, the curator benefited from this very systematic approach. The overall task could be separated into slices of work, and the progress was visible. As a consequence, the individual motivation was pretty high. And what about the performance comparison? Well, this table quantifies the effort spent on both manual taxonomization and the curation of the automatically created taxonomy. We can see that the collaborative human AI approach is efficient, being 5 times faster than the purely manual taxonomization. It is effective since it doesn't require drastic context switching and semantic jumping, since we systematically name clusters and clean groups. It is also scalable, and curation can be parallelized by branch. It is measurable, since we can answer how many branches are left to curate, and it is more systematic than starting with a flat list of concepts. When comparing these two approaches, we came to the conclusion that from a pure working style, there is a significant advantage to start with a draft taxonomy. Instead of being faced with a long to-do list, curators work cluster by cluster, section by section. Even when the clustering fails, the main topic someone is working on remains stable. The following figures show the structural difference between the concept maps of the two approaches. You see that the semi-automatic taxonomization algorithm encourages a strictly hierarchical tree-like concept system. In this study, the proposed taxonomy had only so-called mono-hierarchical relations between concepts. In the manual taxonomization, however, the curator often hooked concepts under more than one parent, creating so-called PolyHierarchical taxonomy. Some concepts can indeed be hooked underneath more than one general concept, but over time, this can lead to quite a multi-linked knowledge net. So why taxonomize? If you still wonder about the benefits of this process, here they are. Taxonomization is an effective way to add structure to data and improve its quality. It ensures easier and safer data maintenance. It is formalization of the knowledge that becomes machine digestible, and it is ready to boost the performance of your AI algorithms. And content, topic, or document classification is just one of the typical tasks that are tackled in industry on a daily basis. In case you need a refresher what classification is about, here it is. The documents we used are predominantly scientific papers in the medical domain related to the COVID pandemic. In their original form, these documents are unlabeled. So in order to label them, for training, we utilized a term extraction tool and got 5 most representative keywords from each document. For each of these keywords, we check whether there was a similar term in our created goal taxonomy. And if it's the case, we would traverse the taxonomy upwards toward the root and find all parent terms of the matching term. Then we would assign the top 2 terms of the parent chain as labels to the document, and after balancing, the final set of distinct document labels had 13 labels. We then split the dataset into training, dev, and test partitions and proceed with supervised learning. And here you can see the respective data split. Before I proceed to performance metrics, I want to show you an example of our data points. Here you see what true labels and predicted labels for the documents look like. And I also want to make an emphasis on the granularity of the labels. So we trained 2 convolutional neural nets, non-initialized one and initialized one with a created taxonomy. For both, we used a word embedding model pre-trained on a PubMed corpus. The non-initialized convolutional neural network had its final dense layer randomly initialized, and the second one had its dense layer initialized with values that leveraged the structure of the taxonomy. The idea is to initialize the final hidden layer with rows that map to co-occurrences of labels in the training data. And this can be implicit hyperlink relations between the labels or explicit co-occurrences in the annotation. For each co-occurrence, a special non-zero value is assigned to the associated classes, and a value of 0 is assigned to the rest. The motivation for this initialization is to incline units in the hidden layer to be dedicated to representing co-occurrence of labels by triggering only the corresponding label nodes in the output layer when they are active. It is a form of embedding the structure of the taxonomy into the hidden layer of the neural network. And zero-shot models were made available by the Hugging Phase, and basically it means that a classifier can make a prediction without prior training examples. It only requires the input text and a set of available labels. Here you see the micro-averages expressed as percentages yielded by our tests. We see that initialized CNN showed the highest score compared to the rest, and we conclude that it has potential. Initialization successfully aided the prediction on the unseen data. Moreover, we can increase this performance, and there are several resources that can be leveraged. This could further lower the effort needed to taxonomize heaps of concepts using the suggested process. Any project revolves around a specific domain that usually features a specific vocabulary, like take virology or medical terms in general for our COVID case. So to create more accurate vector representations for these tokens, the specific context in which they apply must be exploited. A corpus of documents directly related to the domain can be used to retrain or tune word embeddings instead of using a more generic model. Moreover, consistent presence of data, metadata in the terminology can aid the taxonomization process. And if there is metadata about the semantic parent of a term, this valuable information can be leveraged. Definitions of terms can be part of such metadata, and they can describe the type of the given concept. Often these definitions have a certain structure or follow a pattern as well. For example, here we have the term modified live virus vaccine that has the definition vaccine made from an isolate of an attenuated virus. Using NLP tools, we could extract this broader concept vaccine and use it as a parent node in the taxonomy. We believe that the suggested approach can significantly bring down the effort while yielding a taxonomy of a decent quality. And we encourage everyone to try it out if you're looking for ways to enhance the performance of your AI solutions. While our corpus contains English documents only for this study, the labeling process is of course not limited to the English language. For example, at Coreon, we support multilingual concepts. So once the concepts are taxonomized, the knowledge structure is available in all languages and ready to be consumed by your applications without additional fuss. Thank you for your attention. In case you have any questions regarding the presented study, just shoot me a message in social networks. And if you'd like to discover more about our technology and services, you are very welcome to get in touch and check our publicly accessible knowledge repositories that you can play with and explore. Thank you. Bye.